Welcome to Team 12's presentation. Our system is called the Spacebit and Peregrine ecosystem for easy deployment.
The main problem we need to solve within this project is to deliver safely the Moon rover to the Moon surface given the technical specifications provided. This requires weight and volumetric constraints as well as technical, space and lunar specifications. Also, innovating solution without the usage of pyrotechnics is a must. We've also included scarcity of energy in special missions as a key constraint in our design. Some of the ideas and initial designs could be found in the next slide during our brainstorming.
The system will use the Moon's gravitational attraction to accelerate Spacebit from the lander towards the surface of the Moon. It will use a ramp at around 50 degrees so that the Spacebit can roll down onto the surface of the Moon.
In the following slide, we'll see this idea in a more engineering approach, with including secondary control and assistance systems to assist the physical main solution. Also, when talking about the travel box design, it's important to recall that this is fully adapted for launching conditions in Earth, space travel, as well as it is fully integrated to work also as the deployable ramp in our design.
Here you can see the 3D CAD model of the system. Different configurations, enclosed, open, ramp configurations are shown. Here we can see the first sketch for our actual design. We can see the travel box in which the Spacebit is stored along with all of the components and equipment. Here we can see our first sketch of the system in the deployment configuration. The ramp is fully extended and the Spacebit is going down the ramp. Here we can see the ramp after Spacebit has left. It will be left on the Moon in this configuration.
The mission starts on Earth with the launch. It will then travel through space to the Moon. It will then land on the Moon, then the deployment system will begin. The door will disconnect, lowering and extending the ramp. The Spacebit will then lowered by a security rail until it reaches the end of the ramp. It will then activate and start the mission.
For the system materials, we have chosen to minimize weight. The structural materials include carbon fiber reinforced polymers, aluminium, and open cell foams, all of which share in common a very low density. For covering materials, we have chosen MLI foil to protect from solar radiation and PTFL, which is Teflon covering, to make sure that the ramp is as slippery as possible.
The final overall weight of our design resulting being between 0.65 and 0.7 kilograms. Also, recalling the size of our design, it is meant to be 16 per 15.5 per 15 centimeters, being substantially smaller than the initial specifications.
The system has a good set of subsystems duplication. There will be a duplication of motors and servos so that the system will accomplish motion. In case of failure, there is ramp integrity assured by rods and bearings, and there is also a wedge at the end of the ramp, including a security rail so that the Spacebit will not accelerate down the ramp at a fast velocity.
The speed system has future application as it is also compatible with wheeled vehicle or dual leg system in a safe and efficient system.